So the solution we've gotten up to this point, the sum of a sine and a cosine, is a generic solution to our x part of the classical wave equation. But what we want is a solution for our specific case where we have our specific boundary conditions. So what we need to do now is apply those boundary conditions to get our specific solution. All right, and so if we remember our boundary conditions, it's that. And so here we're going to look at just the x part, of course. We know that when x is equal to 0, the displacement has to be 0. The string is fixed on one side. And we know that when x is equal to L, the displacement also has to be 0. So let's look at this first one. So we have a combination of a sine and a cosine. Let's look at cosine of 0 and sine of 0. Cosine of 0 is equal to 1. That's just what cosine is. And sine of 0 is equal to 0. Well, our solution is the sum of a sine and cosine, but this can never be 0. So that means instead, if the cosine part of this term right here, this part can never be 0 because it's always equal to 1 by definition. That means that our constant a has to be equal to 0. And so our solution ends up being only composed of this second part. And so this is how we narrow this down. So we only have the sine part that's left behind. Now let's use the second boundary condition. So we know that x of x is equal to b sine beta x based on the first boundary condition. The second boundary condition says that when x equals L, this also has to be equal to 0. Now let's look at this. So we know that, we can plug in the value of L. So we know that, if we don't want this to be a trivial solution again, we know that b can't be 0. Because if b is 0, then we just end up with our string not moving at all, and that's boring. So that means that our sine beta x term has to be equal to 0 when x is equal to L. So let's go ahead and plug in L for x. And that's not a c, that's parentheses there. So we can say sine beta times L is equal to 0. Now, let's look at the properties of a sine function. So if I draw out a sine function, if we call this x on our axis here, so x equals 0 and increasing here. A sine starts at 0, increases and then decreases, goes down like this and keeps going, etc. Now, if we remember properties of sine functions, so at x equals 0, sine is equal to 0, and at x equals pi, the sine is equal to 1. Oh, that's not right. S equals pi over 2, sine is equal to 1, or 90 degrees, but we're thinking in radians here. When x is equal to pi, that's when sine goes to 0 again. Sine goes to negative 1 when x equals 3 pi over 2. And at x equals 2 pi, we've completed one cycle, and we get back to 0. And so what we see is that the only time sine is equal to 0 are at integer values of pi. Sine times n times pi is equal to 0, where n equals 0, 1, 2, etc. Only for integers. Okay, and so we need to, so the only way that this boundary condition is satisfied is that beta L has to be equal to n times pi. And so we want to solve for beta here. We know L is the length of the string, n is just integers, pi is pi. So we can say that beta is equal to n pi over L. And so our final solution here for the x part is that x of x is equal to our constant b, whatever that is, sine n pi x over L. And this is our solution to the x part of the wave equation. Now, what does this look like? So what these look like, if we kind of draw out our string, if we have, say, n equals 1, we'll end up with a string kind of going up and down like this. Now, we don't know how this evolves in time yet. For n equals 2, we'll get a complete revolution of our sine wave. And this is a whole set of solutions where n equals 3, we get up, down, something like this. And so we'll see a continuation, right? We just get more and more of these waves that fit in between our walls. And so this will, but it only can vary depending on integers. And so this is kind of similar to what we were seeing with the quantized behavior that we were talking about in chapter 1. These integers show up again. And so in the next video, we'll look at what the solution of the time part looks like.